Good morning, students. I hope everyone is back home safe and sound. Please stay safe, stay alive. That should be the motto right now. But at the same time, we have to do what we have to do. So our classes will be continued in the online mode, which I think is good right now, looking at the situation. So as I had discussed earlier, that most of the classes would be recorded lectures, video lectures, because there are many times when students are not able to attend the class because of network issue or some other reason. So I decided that I would go for recording like this one, and then many of the lectures would be from the previous year, that is the classes that I had with your seniors, your immediate seniors, because I feel there is no point recording the same thing again. But then again, because we will have doubts, we will have questions, so I will try my best to schedule as many classes, live classes as possible. Now these live classes will be mainly for clearing doubts, if you have any questions you can ask me there. Okay, so before you join those classes, I would advise, like always, be regular with the video lectures and go through the videos thoroughly, and then if you have questions, it would make sense to attend those classes. Okay, so up to midsem we had done we have finished stack. I did recursion in the class. Tower of Hanoi I could not do, but that is just one example that I left out, which uses a stack, right? So we will continue with queues now. So queues would be the last of the linear data structure, and then we will move on to nonlinear data structure. So let's start with queues first. So queues, like everybody knows, it's a FIFO data structure. So queue is a FIFO data structure. So the first one that comes in is the first one to leave the queue. So queue could be like, if this is an ATM machine and there are people like this, so you see this is the first person to come to the ATM, so he will get access to the ATM first, the ATM machine, and then this guy joins in later, so he gets added to the rear of the end. Okay, fine, like this. So we are adding people. Now if at some point of time, if this is a queue, every queue will have a front and a rear part. Okay, now people will get added from the rear. Okay, like if there is another person coming in now, he will get his position right here. Okay, not here, right? That would not be fair, because this person came in first and this was the second one, and so on. So addition of items or addition of people will be happening from this end of the queue, and people would be deleted or removed, or people would get the service that they are waiting for from the front of the queue. So this one gets access to the ATM machine first, and he's like out of the queue. Okay, so once he is out of the queue, the front one becomes this one. Okay, so every time the front element gets access to an ATM machine, or it could be the processor, it could be anything, right? The items could be anything. So that front element needs to get deleted or removed. That will be happening from the front end, and whoever was the second in line becomes the first in the queue. Okay, and similarly, if elements or people or processors, whatever, right? It could be queue can be used in so many applications. So those who are getting added later on, they will have to go to the rear end of the queue and wait for their turn. So this is something all of us understand. And by first in, first out, what we mean is whoever got into the queue first will be the first one to get the service and go out, right? And the second one gets his or her turn next, and so on. So this is the basic definition of a queue. And like all data structures, this also has 3 primitive operations. Primitive operations means the main operations. Like if you remember, in stack we had push and pop. Okay, so in queue we have enqueue. Enqueue is like adding into a queue, adding an element into a queue. Then just the opposite of that would be dequeue, which is removal of an element from a queue. Fine. And then one more primitive operation could be check for emptiness of a queue, right? So there can be many other functions, as we have seen. There can be display function. There can be a lot of other functions, additional functions that we can define for a queue, but these are like the primary ones. Without these, you cannot really implement a queue. So enqueuing will be happening from the front, like I said. Okay, all addition, all insertions of elements will be happening from the front of the queue, and deletion or dequeue will be happening from the, all additions and deletions will be happening from the rear end of the queue, and deletions or dequeue will be happening from the front end of the queue. Fine. So now let's talk about how to implement a queue. Just like any data structure that we have studied till now, we have mainly 2 options. So implementation can be done either using arrays or linked list. So which one would we prefer? Now here you need to recall what are the advantages of arrays over linked lists, and similarly what are the advantages of linked lists over arrays. So the main limitation of arrays, the negative point about arrays was mainly to deal with the size of the queue or size of the data structure, which is kind of restrictive, right? But in linked list you can keep on adding any number of nodes. Okay, so you don't have to ask the user how many nodes you are going to add in the process, because that could be something very dynamic depending on the application where you are using that this program. The problem with arrays is you cannot really keep adding new nodes or new elements into an array. Okay, every array has a fixed length. It could be quite a big length array, but still it would be of fixed size. Now with linked list, that is very, very flexible. Okay, so that's the main advantage of linked list over arrays. Now coming to the advantage of arrays, if you remember, it's the random access. Okay, given the index, you can randomly go to any element in the array. But in case of a linked list, you have to traverse through the entire list. Okay, and only then you can get to the node which you are interested in. So these are some of the points that we already know. Okay, now depending on this, we might not have a very clear winner in case of a queue implementation, because you see, yeah, there are a few more points that I should be reminding you. In an array, if you remember, deletion or insertion from the front, okay, it's always an expensive operation. So like if this is an array, so on. So if we are adding elements like 10, okay, 20, 30, let's say 40. Let's say these are 4 elements in an array. Okay, they are there already. And then if I ask you to add 50 to the first one without affecting the first one, meaning without removing the first one, that is 10, from the list, what will we need to do? We will need to shift everything right to the right, and then only we get a space here where we can insert 50. So it would result in a list where the elements would be 50, 10, 20, 30 and 40. So insertion or deletions at the front or from the front end of an array is always an expensive operation. Now if you were to delete or insert at the end of from the rear end of a list, or rather an array, that is a constant time operation, right? Because we know the index number of the last element, and we can use that for a constant time operation. Now the problem with queue is we are doing operations at both the ends, right? We are adding to the rear, which makes array a good choice, but again we are deleting from the front. Now if you were to just delete from the front without shifting the elements to the left, okay, I hope I'm clear. Here I have discussed addition of element to the front. Let me just explain deletion, because that is what we are interested in right now. So if we were to delete, if we were to delete 10, okay, then one way of doing that is I can simply put the index, or rather start the index at 1 instead of 0, okay, which I can do because additions we are doing at the end only. So this index number doesn't really change. So it's 4 now, next will be 5, 6, 7 and so on. So it's not really a problem. So insertion is not really an issue with an array implementation. And again, if we are not shifting the remaining elements of an array to the left after every delete operation, then again array is a good choice for queue implementation. Fine. But if you were to shift to make a space, see what will happen is, let's say this is a queue, okay, let's say this is the front element, F for front, this is 20, 30, okay, let's say rear is at 30 now. Fine. Let's add 40. So where will we add 40? 40 will go here. Before you can do that, what we need to do is wherever R is pointing to, what is it pointing to? If I just write the index number here, R is right now pointing to 2, okay? R is basically the index number, right? So before you can add something to the array, okay, to the queue rather, which is of course internally implemented using an array, you need to increment this first. So we'll be doing plus plus R, fine, and then whatever is the array, let's say this is, the array name is Q. So we'll be doing Q Q, then pre-increment, right? Q, pre-increment R, and insert 40 to that. So basically this will be going here, and we will have 40 here. Okay, so this is how we add an element to a queue. Now let's talk about deletion. So how do we delete? How can we delete if we were using arrays? Now, like I said, shifting is going to be an expensive operation, right? So if you have only 3 or 4 elements, that is absolutely okay, doable. But of course, we have to think about real life implementation. So if you were to implement a queue using an array where the number of elements could be in thousands, okay, every time you delete the front element, that is, that is the condition for a queue. Deletion can be done only from the front side, and that should be the first element of the queue. So every time you delete the front element, and if you need to shift so that you have enough space in the queue, then you are basically looking at big O of n. Okay, so deletion from the front and shifting will need a will result in a complexity of big O of n, because if you have, like, where n is the number of elements. Okay, so this is really an expensive operation. Adding to the rear is absolutely easy. You see here, this is Constantine operation, right? You just increment r, and without thinking about anything else, you just say q and r, the updated value of r, just assign 40 to that position. That's it. It's as simple as that. But for deletion, if you delete from the front and shift every remaining element to the left side, that is an expensive operation. So if we want to use arrays to implement q, we should not be shifting elements to the left. Okay, because that would be like so expensive that it would make our implementation very, very slow in real life implementation. Okay, so what do we do then? So deletion, let's delete from the front. Okay, so the front element is 10. Now how do we delete in an array? Now deletion is very simple. We just have to, let's say, delete 10. You don't even have to specify 10. It's always the front element. You cannot delete any random element. Okay, that can be done in an array, but we are talking about q. Okay, even though we are using an array for implementing q, but we have to respect the conditions that make up a q. Okay, so q says that only the front element can be deleted and insertion can be done only at the rear end. So addition we have already discussed. If I say delete 10 or delete from the front, what we can do is we can simply say plus plus f. Okay, increment f. Basically f was pointing to index 0. By doing pre-increment, I will just make f point to 20. So even though 10 is there, okay, if you remember our discussions from the previous classes, in an array elements can be there, but what matters is like in this case, what will matter is if you want to display how many elements are there in the array right now and which are the elements, you just have to run a loop from f to r. So f is pointing to 20 and r is pointing to 40. If you run a loop starting from f and ending at r, you will see 20, 30, 40. Even though 10 is there, you can see it on the screen right now, but it won't be accessible, right? So this is a solution that we will be using to implement a queue. So we won't be shifting. Okay, just keep that in mind. So I hope up to this much things are clear. Now there is going to be a problem here. Okay. So it's 10, 20, 30, 40, right? Okay, let me go to a new page. 10, 20, 30, 40. This was the original array, and the array is also kind of saturated now. Let's say our array, or rather the queue, was only of 4 elements. Okay, the maximum size was 4. 0, 1, 2, 3. So yeah, let's bring back the pointers. R is pointing to the 4th element, that is index number 3, and F is pointing to 20. So basically this thing is not even existing, right? 10 is not there. Even though it's there, we are not going to access it. So now let's keep deleting. So what we learned for deletion was simply increment the pointer. So if I say delete one more time, that is delete 20. You don't have to specify 20 because that's the default. So to delete this, what we need to do is we just need to increment f to the next index, right? So right now, if you were to print out the queue elements, you will see 30 and 40. Okay, let's do it one more time. Delete 30. So that is basically another increment. So f was pointing to 2, now f is pointing to 3. Okay. Now because we have one more element left, we will say delete 40. Sorry, ignore the semicolon, it's not really part of a program. Okay, it's just a statement. Now this is what we will be doing in. So basically these things you can write inside a loop. Okay, if you were to delete everything in the queue. So if I say delete 40, where will f go to? F is right now pointing to 3, right? So increment will take it to 4. Okay, so now f is pointing to 4. 4 does not even exist, by the way, this is deleted. Okay, so with this, f is actually, the value of f is actually not assigned. So this will result in a value of f equal to 4 and r equal to 3. Okay, now done. Now you see, just look at the queue right now. Okay, ignore f and r, just look at the queue. What are the elements inside the queue? There are no elements, right? These are all empty. The queue is actually empty because we have deleted everything. So logically I should be able to add another element here, okay, into the queue. But because now if you do, what was the code for adding? You see, you need to pre-increment r, okay, and then use that as an index and assign the new number. The problem is, if you increment, or rather pre-increment r will also be, like if I want to add 50, okay, so I'll be doing pre-increment r. Now this will result in r being, instead of 3, it will be now 4. Now you see, there is no index called 4. Our array is a very small array. Sorry, I keep saying array, it's actually queue implemented using an array. So our queue is actually of only 4 elements, right? So max size is, if I say max size is only 4. So if you ever, in the process of addition and deletion, or NQ or DQ as we call it in terms of queue, in the process of NQing and DQing, if you ever reach to these values where f and r, they are equal to max size, okay, if f is equal to r is equal to max size, okay, then it means that the queue is full. But you see, the queue is actually empty. So this problem is coming up simply because when we were deleting the element, we were not shifting it, right? So every time you delete, if you had shifted all the elements one time to the left, even though that would be a really expensive operation, but if we were to do it after all these deletions, deletion of 10, 20, 30 and 40, we would be basically looking at this, and you could have actually added more elements. I mean, theoretically that is what we should be able to do, because queue is not full. But what is the conclusion right now? Queue is full, because we are working with an array, and we are working with these 2 pointers, front and rear. So program wise, you won't be able to add any more elements into the queue. So this is one big problem that comes up when we use an array for implementing a queue. So let us do a quick recap of the things that we just discussed. We have already understood what is a queue. We have understood these operations, NQ, DQ, okay, and we were talking about implementing using an array. So now with an array, insertion or addition of elements into a queue is, it's a very simple operation. There's nothing to really discuss about. It's a constant time operation. But when we talk about the deletion, we have two options. Okay, when we delete using an array implementation, one option is to shift. Every time you delete, shift all the n minus 1 elements to the left. Okay, every time we delete one element, you will have to run a loop for at least n minus 1 iterations. That is an expensive operation, so we say we don't want to go for that. So without that, what happens is we simply move the front pointer, okay, one at a time. Every time I delete, I just increment it. Okay, now that works fine as long as this situation doesn't come up. Okay, so there will come a time, it doesn't matter how big the size is. Max size is 4 right now. You could make it 4,000 or 40,000, it doesn't matter. There will come a time, if you have done too many of delete and insert operations or DQ or NQ operations on a queue, okay, there will come a time when you will reach this situation where the queue is actually empty. You know, it has many spaces, I mean all the max size worth of space remaining there, but we are not able to add anything because our condition, which uses front and rear pointers to check, it will tell us that queue is full when the queue is actually not full. Okay, so just keep this in mind. So I'm not saying that we should not be implementing an array, a queue using an array, but this is a problem that we have to consider. Okay, let's quickly talk about a linked list implementation. Now, how good or bad will be a linked list implementation? Okay, so if we go for a linked list implementation, if you guys remember, linked list looks like this. Okay, now you can have a singly linked list, you can have a doubly linked list, and so on. This is the header node. So let's say we have 10, 20, 30. Now let's talk about adding a new element to the queue. Let's say this is the queue, okay? This is the front. What is front? Header next, okay? What is rear? That would be the last node. Okay. So if you want to add an element to the end of the queue, okay, that is the process. So you will have to basically traverse through the entire list, or you can keep a pointer pointing to the, so it's an additional thing that we have to keep in mind. Okay, so you have to implement, if you were to implement using linked list, you will need to keep an extra pointer that points to the last node every time. Every time you add a new node, you need to update this to that one. Okay, fine. And what about deletion? Deletion should be simple because it's at the front. You know, that's where linked list has an advantage over arrays. So deletion should not be a problem at all. So wherever f is pointing to, or header next basically, right, you just delete that node. Before you do that, of course, you need to connect header next to the next node, or basically move f like this. So linked list can be used to implement a queue, obviously. Okay, but then again, you have to keep track of the pointer, the rear pointer specifically. And if you don't do that, you will have to do traversal every time you were to add a new element to the rear end of the queue. Okay, and of course there is an extra 4 pointers per node, you know, for the, not 4 pointers, sorry, 4 bytes. I'm really sorry about that. 4 bytes, extra 4 bytes for the pointer variable. So if you are, you know, if you have a node which contains an integer data, which is also 4 bytes, right? So in a linked list implementation, every node will have an additional 4 bytes for the pointer variable. So it's basically looking at double the size compared to an array. Now these sizes for a small number of elements do not really matter, but if you think of large numbers, really large numbers in a list, then obviously these, because it's double the size of an array implementation, we have to think about the additional 4 bytes also. So both arrays and linked lists can be used, okay, the way I have discussed. For this class, I will be going for the array implementation first, okay, and then I'll talk about, we have already discussed the problem here, okay, we'll try to solve that in the array implementation only, and the linked list part I think you guys can also try out as an assignment. Okay, now let's have a look at the implementation of a queue using a doubly linked list. So now a queue needs 2 pointer variables. So we are not really talking about a pointer variable that points to an address, okay, but these are just names that I am using here. So as you can see, we need a structure here. We have done this kind of implementation many times before this. So I'm going for a structure, doing a type def, renaming the whole thing into a queue. What do we have inside the structure? We have an array, okay, because basically we are using an array to implement the queue. And yep. And max queue size I've put to 5, you know, just to run this program. You can give any size here. Yes, so inside the structure we have the array and the front and rear, okay, and we rename the whole thing as queue. And then we have a few functions: insert, delete. Insert is basically enqueue and delete is dequeue, and then we have the empty function and display function, okay. So next we go to so let's talk about the insert queue first, insert function. So the things that we need is obviously the array, okay, so that we are, because see this whole thing is the array is inside the structure, so we are passing the structure as an address. Why? So that we end up passing only 4 bytes instead of, you know, many bytes. So again, explained many times in the previous classes. So I'm passing a pointer variable here, and this int is basically the size of the elements in the array or the queue right now. Display, same. Oh, sorry, for insert, this int is basically the element that we are adding. Now next is the display function, which has only one argument. Again, the structure, or rather the queue structure, has to be passed as an address. Then delete, same. You don't have to specify which element to be deleted, because, you know, it's a queue, only the front element can be deleted. And lastly, we have the empty function, which will return true or false, which I have already defined here. True is 1 and false is 0. Okay, now let's look at the function definition. So let's go with the insert first. So before we can add any element to the queue, we need to check if it's full or not. Again, this thing is coming up only because we are using an array, okay. By definition, a queue should never be full. It can be empty, but it should never be full, okay. It should have unlimited space. But because in real life we have to use either array or linked list, and because this program is using an array, so there will be a limitation as far as the number of elements inside the queue is concerned. So how do we check if it's full? Now this I had already explained. If queue rear, okay, if queue rear is basically the rear pointer, is greater than or equal to max queue minus 1. Okay, let me quickly take you back to this slide. The next one. Oh, let me just write. So when we had even if you don't delete anything, you see, just ignore the arrows coming from F. Okay, just look at R. Where is R right now? R is at 3, right? What is 3 actually? It's max size minus 1. So what is the situation right now? The array is actually, or rather the queue is actually full now. You don't have any space to the right anymore. Okay, I hope everyone is understanding this. So this is the condition I'm using in the program. So if R is equal to, or it can even be greater than, right? You see, it was 3 here, then if you attempt to add another element when the queue is actually full, then R can become 4 also. So we are saying if R is greater than or equal to 3, how do we write 3? Max queue minus 1. I have written max size here, but in the program I have written max queue. It doesn't matter, it means the same thing. So if R is greater than or equal to max queue minus 1. Okay, let's go back to the program. Yeah. So if R is, or rear is greater than or equal to max queue minus 1, then the array is, or the queue is full. So you say printf overflow or something like that. Okay. Else, it means there is some space, even if it's just one space or many spaces, doesn't matter. We just need one space, right? So what we do is, again going back to this, what do? We pre-increment R. Remember this example? R was originally pointing to 30, and when I said add 40, okay, first we did pre-increment. We made R point to the next box. So basically we incremented index 2 to 3. So that's pre-increment, and then we use that as an index in the array to assign the new number. So it's Q plus plus R. Okay, let's go back to the terminal. So Q items, because the array is actually called items. You see here. Okay, the array name is items. So we just need to write Q items plus plus pre-increment the rear pointer, and assign whatever number is being added. Okay, so everything is based on what we have just discussed. So this is for the enqueue or insert operation. Now what about the display? Display is from front to rear. Okay, so here we are saying if the queue is not empty, if the queue is empty, there's nothing to print out. So otherwise we just have to run a loop from queue front to less than or equal to queue rear. Okay, and in every iteration we will be simply printing off queue items, and in the index we will be using I. I hope this is clear. Okay, just think in terms of F and R, so when you are doing this on your own, draw a picture in your notebook, put some elements there, put F and R properly, F pointing to the front element, R pointing to the rear element, and do the operations from enqueue, dequeue, insert, delete. Okay, then you will understand it better. It's a very simple code. Okay, now what is this empty function? When will a queue be empty? So for that we will have to go back here. Just one second. See, at the beginning we are doing an initialization. Okay, we say that front should be first initialized to 0 and rear should be initialized to -1. Okay, so this is what we are using in the empty condition. So this is like at the beginning, right, when the queue is actually empty. So q dot front is equal to 0, is assigned 0, and q dot rear is -1. So rear is less than front. That is what we are using here. Rear is less than front. So this is like at the beginning, no? Let's talk about a different situation. say we have 10, 20 and 30. Let's say we have few more spaces left, so this would be F, this would be R. Okay, now let's start deleting. So how do we delete? We just increment F. So F will now be pointing to 1. So this is 10 is kind of deleted. Okay, let's delete it one more time. Just increment F to 2. So 20 is gone. Fine. Now F and R are both pointing to the same element. Okay, let's delete it one more time. Basically, let's increment F to, from 2 it goes to 3. So right now F is 3 and R is 2. Okay, so R is less than F. What is the meaning of this? It means that the queue is empty. There are no more elements, right? I hope this is clear. So rear is less than front. Yep. So rear is less than front. So like we can use this condition at the beginning of the program also, where we have initialized front to 0 and q rear to be a smaller number, that is -1. So that time also this condition stays true, because rear is less than front, and even while the NQ and DQ operations are in process and the queue still has some space left, this condition will still hold true. So I hope this part is clear. So to check for emptiness of a queue, we just need to compare the rear and the front. So if rear is less than front, we say the queue is empty, otherwise queue is not empty. Okay, it doesn't talk anything about queue being full, because to check for the fullness of a queue, this is the condition. Okay, rear should be greater than or equal to max q minus 1. Right, and this empty function is what we use in the display function also. Okay, let's go to the last function, that is delete. So what is this delete function? Again, here we first check for emptiness, because now this is something we should be checking. Checking for underflow is mandatory, because the queue can be empty, right? If the queue is empty, we should not proceed with the delete operation. Now checking for overflow, that is queue is full, is not really a legal operation, like I told you earlier, because queue is never supposed to be running out of a space, but because of array implementation we have that problem. Okay, but that is not true in case of a empty operation. So empty function is a valid and a legal function, because a queue can be empty, and this is useful when you are trying to delete or print. Okay, so if the queue is empty, we say underflow, there is nothing to print out. You can put some more printf messages here, like the queue is empty, something like that, more interesting, more meaningful. If the queue is not empty, then all we need to do is, you see, we are returning something here, because we would like to see what was deleted, but you can make it a void also, doesn't matter. It totally depends on how you are going to use the delete function. So because I put an int here, the return type, so that's why I'm returning that item that I have just, this is queue items, queue front, this is item, the front item, right? I've just returned this. Once you have returned it, the main operation, if you remember from our discussion, is to increment the front pointer. That's the key operation here. Returning is an additional thing. You may or may not return it, that is not really important. What is important is the increment part. It should be a post increment. Okay, so q front plus plus. Okay, so that's all. And in the main, I'm just checking out this function. So I call insert 1, so I'm adding 1, then 2, then 3, then 4, then 5, then I'll display, and then I'll delete once. Okay, so this line will say deleted item is whatever. So what would be the deleted item? look at the order in which we are adding. So we added 1, then we added 2, then 3, then 4 and 5. 5 was added at the end, right? It's a FIFO list. First in, first out. Which element came first? It's 1. So when I call the delete function, 1 should be the one, number 1 should be deleted first. And then if I display, I should see 2, 3, 4, 5. I should not see 1 anymore. And so on. Okay. So just keep this sequence in mind. So the first time I do a display, I should see 1, 2, 3, 4, and then I should see 1 being deleted, and then I call the display. I should see 2, 3, 4, 5, and then I insert 6, and then I display. So it should show me 2, 3, 4, 5, 6. Okay, so you can play with this. You can keep on adding and deleting. So you need to write this program on your own. So while you're watching the video, just stop it at appropriate moments. Take a screenshot or whatever. Okay, write it in your notes. That would be useful, and then type it and run it in your program, in your computers. Okay, for now let me just run it. ccq1.c. Okay, done. So you see 1, 2, 3, 4, 5. Then deleted item is 1. Then 2, 3, 4, 5. Oh, we are not seeing 6, right? Because if you remember because the max queue size was set to 5. Okay, and because we were not shifting, so as far as the rear pointer is concerned, it thinks that the queue is actually full, but actually the queue is not full because we just deleted 1, no? So the first element is actually free, but we are not able to use it. Fine. So we can see an overflow error here. So this is a problem that we will try to solve in the next lecture. Okay. So you can for now you can simply change the max queue size to maybe 7, 10 or whatever, something bigger than 5, so that you don't get the overflow error. You should get it. I mean, it's good. It's a good check. It's telling that the program is actually working. So you see, when I increase the size to 10 or whatever, 2, 3, 4, 5, 6, 6 is also getting added, right? So the program works. So what I'd like all of you to do now is go through this lecture, understand this very well, and if you have questions, post it in Microsoft Team or maybe in our WhatsApp group. Okay. If I can answer then and there, I will do that. Otherwise, we will have a live session on this. So this is for everyone, okay? Everyone in the class. All of you have a lot of time now. So please use this time efficiently. You are with your family members. Some of you are still here, but you will have to go back, right? We have an order that has already been circulated. So once you reach home, make sure you go through this lecture and let me know before the end of this week. Okay then, so we stop here for now, and yes, I will wait for your questions and feedback. Okay, so have a great day, have a good day, be safe. I'll see you in the next class.